Hello, Mr. Green here. I'm going to take you through the next section of the forces topic of the AQA GCSE Physics. Topic today is velocity time graphs, and our learning objective is to read and interpret velocity time graphs. Please pause the video and take that down as your title. Okay, so we're going to start as we normally start with some retrieval questions. There are 5 questions on the board. Please pause the video and attempt those questions and restart when you'd like the answers. Okay, so question 1. What's Newton's first law? Newton's first law states that an object will continue to stay at rest or move with uniform velocity unless a force acts upon it. So basically things continue what they're doing unless a force acts on them, a resultant force acts on them. Question 2. What's Newton's second law, and an equation will do for this? Newton's second law states force equals mass times acceleration. Question 3. What is the force an object experiences if its mass is 30 kilograms and acceleration is 18 meters per second squared? Use the equation we've previously seen. Force is mass times acceleration, so that would be 30 times 18, giving us 540 newtons. Question 4. What's the acceleration an object experiences if its mass is 15 and experiences a force of 50? We need to rearrange the equation, so that's force divided by mass gives us acceleration. That's 50 divided by 15, giving us 3.33 meters per second squared. Question 5. What is the mass of an object if it experiences a force of 10 newtons when accelerating at 5 meters per second? So again, we rearrange the equation to work out the mass. Force divided by acceleration gives us mass. So that's 10 divided by 5, 2 kilograms would be the mass. Okay, learning outcomes for today. We're going to interpret a simple velocity time graph, state the motion of an object based on a velocity time graph, and to calculate values of acceleration from velocity time graphs. So we're going to start by looking at this graph, and each graph would start with an axis, and this axis must contain 3 things. It must contain an appropriate scale that goes up in equal intervals. It can't just jump around in random intervals. So on the graph we've got there, the bottom scale goes up in 10s and the scale on the speed axis goes up in 5s. It needs a label to tell us what the quantity is, and it gives us units telling us what the quantity is measured in. Once those things are on the graph, we can interpret the graph easily enough. So we can tell from this it's a speed time graph or a velocity time graph. So the graph is going to be used to describe the movement of the car below. So, at the moment, the car starts from rest and starts accelerating. Copy down this blank graph and tell me, what do you think the graph will look like once it starts accelerating? What will the line look like? Pause the video whilst you attempt that. Okay, so when it's accelerating, the speed's increasing, so the speed is going up over the time taken. So what we'd see there is a straight line with a positive gradient. So it's going up incrementally, speed is increasing over the time taken. Once it reaches 15 meters per second, for around 20 seconds, the car will then travel at a constant speed. How will the line look at that point? Pause the video and attempt that. Okay, so as the speed isn't changing, as it remains constant, then it will remain constant on the graph. So we'll show a horizontal line with a gradient of 0. On a speed time graph, positive gradient shows acceleration, horizontal gradient of 0 shows us travelling at a constant speed. The speed car then speeds up again with lower acceleration as before. What will the line look like? So for the next 10 seconds, it accelerates even further, but it's at a lower acceleration. What will that line look like? Pause the video and attempt it. Okay, again, as the speed is increasing, we get a straight line with a positive gradient. Because the acceleration is lower than A, the gradient isn't as steep. You can see if you compare the line at A and the line at C, the line at A is much steeper, it's got a much higher gradient. So that means it's accelerating more in A than C. C is still accelerating, just not as quickly. The car then slams on the brakes, so over the next 20 seconds from 30 to 50, it slams on the brakes and comes to a stop. What happens to the line? Okay, as it slams on the brakes and comes to a stop, we'll get deceleration. The car's speed is decreasing all the way down to 0. If it slams on the brakes, it's going to come to rest. So when we go into deceleration, we see a straight line with a negative gradient. So it comes all the way down to 0. So how can the acceleration of an object be calculated from that velocity time graph? We know when it's accelerating, we get that positive gradient, but how can we calculate the acceleration? The gradient of the line represents acceleration. If the gradient goes up, it's a positive acceleration, and if the gradient goes down, it has a negative acceleration or a deceleration. We can now use values from the graph to calculate that acceleration. Using our equation, acceleration is change in velocity divided by time taken. So let's have a look at this object here. Between points A and B, what's the acceleration of the object? So we need to be looking at our graph, we need to be taking values from the graph, and we need to be interpreting them properly. So the object's speed has increased by 20 meters per second. At point A, it's travelling at 5 meters per second, and at point B, it's travelling at 25 meters per second. So 25, the final velocity, take away 5, which is the initial velocity, gives us 20 meters per second. It's taken 4 seconds to change speed. At A, that's at 2 seconds, and B, if we read down, that's at 6 seconds. 6 take away 2 gives us 4. We've now got our change in speed, and we've now got our time. Acceleration is change in speed, or change in velocity divided by time. That's 20 divided by 4. This gives us an acceleration of 5 meters per second squared. So, we'd find the change in velocity, what's the velocity at the first part, what's the velocity at the final part, take them away from each other. We'd find the time, look on your graph and see where the time is, and it's the gap between that we're looking for. Divide the velocity by the time, change in velocity by the time, and we get acceleration. Okay, could you try it for the graph that we've just seen? So calculate the acceleration of the object at A, B, C, and D. Take your values from the graph to see if you can work that out. Pause the video whilst you do that, restart when you'd like the answers. Okay, so for A, the change in velocity is 15, it goes from 0 to 15, and the time taken is 10 seconds. So that's 15 divided by 10 gives us 1.5 meters per second squared. At B, it starts at 15 and ends at 15, so the change in velocity is 0. That would be 0 divided by 10, giving us 0 meters per second. We can tell it's not accelerating because it's a horizontal line. At C, there is acceleration, it's a positive gradient. That starts at 15 and ends at 25, giving us a change in velocity of 10. And the time, it goes from 20 seconds to 30 seconds, that's also 10. So 10 divided by 10 gives us 1 meter per second squared. And finally at D, it starts at 25 and goes to 0, so that's a change in velocity of 25. The time taken is 20 seconds, 25 divided by 10 gives us minus 1.25 meters per second, minus because it is deceleration. Okay, as well as the gradient showing us the acceleration, the area under the graph can show us something else as well. What do we think the area under the graph can show us? The area under the graph tells us the displacement of the object. It tells us how far the object has moved in total. So it can give us an idea of the distance travelled or the total distance that's been travelled as it's gone from A to B and back again. So how do we calculate this? Our first step is to divide the area under the graph into really simple shapes that we can easily calculate the area of. So for the graph that's on the board, I'm going to do those 2 lines in there. I've now separated it out into 2 triangles and a square. From your maths and from other lessons you've done, you should know how to calculate the area of a triangle and a square. Area of a square is the length times the width, and the area of the triangle is half times the length times the width. We'll then use figures from the graph to calculate these. So, for A, B, and C. For A, we want the area of the triangle. That's the base times the height divided by 2. We take our values from the graph. So the base is taking 4 seconds and the height is 7 meters per second. For our area then, we do 4 times 7 divided by 2, giving us 28 divided by 2. The area under that graph represents 14 meters. Try and do B, so please pause the video and attempt B. Okay, for B, it's the area of a rectangle, so that's base times height. Take our values from the graph. So for the base, it starts at 4 and ends at 7. The difference between those is 3. And the height it reaches is 7 meters per second, so that would be 3 times 7, giving us an area of 21. So, and that total, that displacement for that area is 21 meters. Try and work out C. Okay, C again is the area of a triangle, that's base times height divided by 2. Take our values from the graph, so for the base it starts at 7 and ends in 9. That's travelled 2, so for 2 seconds, and the height is 7. So it'd be 2 times 7, which gives us 14. Divide that by 2, gives us 7 meters. So what's the total displacement? We need the area for A, B and C added together. So that would be 14 plus 21 plus 7. The total displacement for that object on that graph is 42 meters. Okay, so pull together everything that we've done in the last few slides. I've given you a graph there, and could you answer those 9 questions for me? Pause the video and attempt to do that. Okay, so for number 1, the maximum speed on the graph would be 10 meters per second. That's the highest number that it's reached. What's the acceleration for the first section? So for the first area where it's going up, it's gone up by 4 meters per second, and it's taken 2 seconds to do that. So that's 4 divided by 2, 2 meters per second squared. What's the acceleration for the second section? We can see it's a horizontal line. No calculation necessary. If it's horizontal line, it would be 0 meters per second squared. What's the acceleration for the third section? We need to look at the graph and take our figures carefully. So it starts at 4 meters per second and ends at 10. 10 take away 4 gives us 6. So the change in velocity is 6 meters per second. The time taken, it goes from 4 to 6. That's 2 seconds overall. So we would want 6 divided by 2, giving us 3 meters per second squared. Okay, question 5. What's the distance for the first section of the graph? Well, we want the area under the graph for this one, and the area is a triangle. So we do base times height divided by 2, but we take our figures from the graph. The base is 2 seconds and the height is 4 meters per second. So that's 2 times 4, giving us 8. 8 divided by 2, because it's the triangle, would give us 4 meters. Question 6, what's the distance for the second section of the graph? Second section we can divide into a square. Total, the velocity would read as 4, and the time taken 2, so that would be 4 times 2, giving us 8 meters. Okay, question 7, we'd need to divide that into 2 sections, a triangle and a square. So, our square reads 6 minus 4 gives us 2 seconds, and 4 minus 0 gives us 4 meters per second. We'd add that to the area of the triangle, which is 6 minus 4, that's the time, divided by, 6 minus 4, times 10, which is the velocity, minus 4, that's the height of the graph. So 2 times 4 plus 2 times 6 divided by 2. That's 8 plus 6, giving us 14 meters in total. What's the total distance travelled? We'd add those 3 sections, the first, second and third section together. So 14, add 8, add 4, would give us 26 meters. What's the total displacement? Well, it's all travelling in the positive velocity direction. It's not travelled any further back, so that would be the same, 26 meters. Okay, quick exam question for us to attempt. Helen and Finn take part in a cross-country run. Look at the information and their speeds have been plotted on the graph. Use the graphs to compare Helen and Finn's acceleration over the whole run. Use data from the graph to do that, and to get a few minutes to do that, pause the video and restart when you'd like the answer. Okay, so we divide the graph into 2 sections, first 900 and second 900. For the first 900, Finn's gradient is much greater than Helen's, so he's accelerating quicker than her, and there's the figures if you work it out. For the second section, Finn is decelerating the same rate he accelerated, that's the same gradient, and Helen's is a level line, she's not accelerating, so again, Finn has a larger acceleration. Okay, I hope you found that lesson useful. Please review the video if you'd like to see any parts of it again, and subscribe to our YouTube channel to make sure you get all of our videos. Thanks very much for your time. Goodbye.